Okay, so in this video I'll be showing you how to optimize a winglet shape that you can see here using HEEDS, Siemens NX and STAR CCM+. So first I'm going to give a quick overview of what's going to happen. So here we are within HEEDS and we can see the total process. So HEEDS is going to supply input parameters that will change the model within Siemens NX. That changed model will be exported as a step file to STAR CCM+. STAR CCM+ will execute the simulation so that we can, so values like lift and drag will be known, and HEEDS will try to minimize the drag and achieve a certain amount of lift. So as you can see here, you can see my parametric model of my winglet. So if I go to expressions, I have the different kind of variables, so I can change, for example, the vertical length to 150, and the shape of the model will change automatically. So I'm not going to show you how to make this model, but there is something that I like to do before I export this model as a step file. I like to name my faces within Siemens NX. So for example, I'm going to name the face of the winglet tip. I'm going to change this back so that I can use a surface control on that face. So to do this, you go to selection filter, select face, then select the face, go to properties, and then right here you can change the name. So I already changed this to winglet tip. So if you hover over this face, it says winglet tip. Now you can also do this within STAR CCM+ using, for example, the split by patch command. But when you use HEEDS, you want everything to be as automatically as possible. So you would have to write or record a Java macro to split the face and name this face. But in my personal experience, those macros don't always work. So I just like to name the face within Siemens NX so that when the geometry changes, the faces will still be correctly named. Okay, so now that we set up our Siemens NX model, we can I exported it as a step file so that we can import it within STAR CCM+. So it's this one, I think. And if everything went right, if we check under surfaces, we can see the winglet, the wing surface, and then the winglet tip. Okay, so now we want to make the domain for the fluid. The documentation of STAR CCM+ recommends a bullet shape. So that's what we are going to make here. So we're going to make a sketch in the XY plane. So you right click this, create sketch. Create a half circle. So as you saw in the CAD model, we only made half of a wing, so we only have to make half of a bullet domain. Now to give this domain the right length, I'm going to change the coordinates of these, but I'm going to fix this one first because otherwise they might change position. So I think the documentation says something about it has to be 8 or 10 times the maximum length of your model. So in our case, that's the wingspan, which is 310 millimeters. So I'm going to make this domain, I think 2.5 meters long. So this point has to be at minus 2.5. this one has to be 0. Oh, okay. That's not good. And this point is already good. So now I have to create the other part of the domain. So we're only going to make like half of the bullet shape so that we can revolve this around this axis. This point here, okay. So I'm going to, in this length, I'm going to make it a bit longer to capture the full flow profile of the wing. So I'm going to put this at 3 meters. Alright, so now we can revolve this sketch. It will automatically select this curve as the revolve axis. So we need to revolve it 180 degrees. It's a solid, yep, alright. So now we have this. Now we're already going to name the surfaces. So this is going to be the symmetry plane. So we can rename this symmetry plane. Now the inlet will be this whole surface. I'll explain later why I do this. This is going to be inlets. This is going to be outlets. Alright, so that's pretty much done, so I can close the 3D CAD. Now, you could also import the winglet model within the 3D CAD, but that will give problems later on because HEEDS uses the replace part command. So if you go here, it will use this command, and you can't use this command within the 3D CAD environment. So that's why I import the winglet model over here, and then we're going to use a subtract operation on those two parts. So the input parts will be, well, I have to make this into a part, so new geometry part. We'll call this domain. Yeah, then new boolean, subtract input parts, those two, and then the target part will be the domain. Perform can boolean, execute upon operation. Alright. So now we have the fluid domain, and that's pretty much the geometry setup. So now that our geometry is fully set up, we're going to create our continua. So we're going to create a physics continuum and select models. So it's 3-dimensional. We're going to, this is a hydrofoil, so it's going to be submerged underwater. So we're going to use a liquid segregated flow. It's going to be steady. I'm going to use a constant density model because it's going to be at low speed, so at low Mach numbers, so we can assume that the flow will be constant density. It's going to be turbulent, and I'm going to use the K omega turbulence model with the gamma transition model. Because we're going to operate at such low speeds, part of the flow will still be laminar, so we need that transition model to accurately predict the transition from laminar to turbulent. So that's the physics setup. I can rename this as fluid physics. Now we're going to assign this to a region so that we can create the mesh later on. Create one region for all parts. Well, we're only using one part for each part surface, so we have the inlet surface and the outlet surface. We can define them more easily. So click apply, and that will create our region. Okay, so if we look at the geometry scene, we can actually see which part will be selected. So we have the outlet, the inlet, which is the big surface here. So in type we use a velocity inlet for the inlet. The outlet will be a pressure outlet. Symmetry plane, well, there will be a symmetry plane. And these will just be walls. So now the inlet. Why do I use this big inlet? Well, I'm going to change the angle of attack within the simulation using the angle of the inlet velocity. So by doing this, when we want to change the angle of attack, we're not actually changing the geometry. So that means we don't have to remesh our part every time we want to simulate another angle of attack. Now to define these variables like velocity magnitude and the flow direction, I'm going to change this into components. I'm actually going to define some parameters. So this will be, for example, velocity, and these will be the components, the velocity components according to the x-axis and the y-axis. So the velocity will be 6.4 meters per second. Now the x velocity will be the normal velocity times the cosine of the angle of attack. Those are also variables that I will have to define. So this will be the angle of attack in degrees, and this will be the angle of attack in radians. So we'll start at an angle of attack of 0 degrees, and then to convert this into radians, we'll have to use that formula. So the angle of attack times 3.14, that's pi divided by 180. So now the x velocity is defined. Now the y velocity has to be defined as well. And this has to be velocity. Alright, so that that allows us to define the velocity magnitude as a variable so that we can change it later more easily. So we have the velocity here, and now the flow direct specification is in components, and we can change it over here. And we're going to use those x velocity and y velocity components to change the flow direction. So now I can just change the angle of attack in degrees, and all of these, the x velocity, y velocity will change so that the inlet direction will be correct. Now an important thing to adjust as well is to change the velocity in the fluid physics. So because this parameter will only change the state of the inlet velocity. It will not change the state of the fluid within a domain. So right now the fluid within a domain will be still. It will not move. So that will cause the simulation to converge a bit slower because it has to accelerate all this fluid within a domain. So if we give the fluid within a domain an initial velocity, the solution will converge much quicker. Okay, so that's the fluid physics. The region is also fully set up already. So now we can create the mesh. So we create an automated mesh, and we're going to use this on the subtract. Surface remesher, sure. Automatics. Going to use a polyhedral mesh because we're going to change the angle of attack using the velocity inlet. So the polyhedral mesh will be better to handle those velocities from different directions. And we're going to also use a prism layer. Okay, so the base size, I'll have to check my other simulation for that. So I'm going to use 0.31 meters. Target surface size 1%. Minimum is 0.1%. These are things you'll have to research on your own. These are far from optimal, I think, but they worked. Surface growth rate, I'm going to put this to slow. Number of prism layers will be 15. Prism layer stretching. Okay. The total thickness. I'm going to use the absolute thickness. These are calculated using formulas. You can also find calculators online to calculate the parameters for the prism layer, which are actually pretty useful. The volume growth rate, I'm also going to put this to 1.1, which is the same as the surface growth rate. So its surface growth rate of slow is equal to 1.1, if I'm not mistaken. Okay, so those are the default controls. Now we have to define some custom controls. So I am going to create 3 surface controls and then 1 curve control. The curve control will be the trailing edge. Now I haven't created the trailing edge yet, so I'm going to do this right now. And I'm going to record this. So I'm going to record a macro to split these edges and name the trailing edge. That macro will be used in HEEDS because when you replace this part with a new model, it will not create the trailing edge by itself. So I'm going to here click start recording. I'm going to give this a name, split edges. I can't use space. Okay, save. So I have a few options. The thing that worked for me the most is split at junctions. And then edge number 2, I'm going to rename this to trailing edge. Okay, and I can combine these again. Okay, now another important step is to execute the subtract operation within the Java macro. So I'm going to stop the recording here because I had quite a bit of problems when I didn't do this. Because when you click mesh, it will execute the subtract and the automated mesh pretty much simultaneously, I think. And if we, I'm going to use a filter to select the trailing edge. So I'm going to do this now. So I'm going to sort that name contains trailing edge. So as you can see, it selects the right one. I'll click OK. So if you do not use the subtract operation, it will not recognize the trailing edge for some reason. So just execute the subtract operation within Java macro and you won't have that problem, I hope. Okay, so for the trailing edge, I'm going to change the target surface size to something else. That's going to be custom target surface size. Let's say 0.05. Now, the different surface controls. So I'm going to have a symmetry surface control. I'm going to have a surface control on the winglet tip. And I'm going to have a surface control on the outer boundaries. So the outer boundaries is going to be the outlet and the inlet. I don't think I have to use filters for that. Nope. So the mesh can actually be much coarser near boundaries. It can be the same size as the span of the wing. So target surface size is going to be a custom control, and it's going to be 0.31 meters. So that will make the mesh a lot coarser near the boundaries, and it will save a lot of computer resources. Also going to disable the prism layer mesh. So I'm going to disable this. That's pretty much it. And now the symmetry plane. We will actually have to change the surface growth rate. Because we have to change the surface growth rate so that it is the same as the volume growth rate. Because otherwise it's going to be a mismatch between the two. So I'm going to select the symmetry plane here. Target surface size is going to be custom as well. Prism layers will also be disabled. So the target surface size is going to be absolute 0.31. That was absolute, that's not right. Surface growth rate was slow, so 1.1. And I think that's everything fully set up. Oh, we have to change the winglet tip. We're doing this because, like a general rule of thumb, I think is to have 100 cells in the chord direction. So because the chord here at the winglet tip is much smaller, we have to refine the mesh here as well. So I'm going to select the winglet tip, controls, target surface size, custom, and I think the target length is 30 millimeters. So the absolute target surface size is going to be this value. Okay, so that's the mesh, the region, and the physics pretty much fully set up. Okay, so apparently I'm having trouble defining the velocity as a parameter. I don't know why it's not working, but it doesn't. So you just have to change the parameters to the actual value of the velocity. So here x velocity, y velocity, and also the velocity magnitudes. You change that to 6.4, and then it should work just fine. So here you can see our mesh. For demonstration purposes, I made it a bit coarser just to speed up the process. So now we're going to define the stopping criteria. I'm going to put this to 400 steps. And now I'm also going to create a monitor criteria. Okay, no, first I have to create the reports. So I'm going to have a report for the drag and the lift, obviously, because those two are pretty important for this study. So I'm going to call this lift, this one drag. Now, for the direction, you really have to be careful, because when I first set this up, I just put lift like this, 0, 1, 0. So according to the y-axis, and drag according to the x-axis. So I thought, well, that's going to be fine. Well, that's not the case, because when we change the angle of attack, we actually change the direction of the velocity. And the lift that's just the definition of lift. That's the force perpendicular to the direction of the velocity. So when the direction of the velocity changes, you also have to change the direction of the lift. Because if you don't do this, you will get negative values for lift, negative values for drag, and the values will just be completely false. So now to define the direction, we can actually use the parameters x velocity and y velocity that we defined earlier. So the drag will be defined like this, and the lift will be defined like this. So that fixes the problem of having negative values for drag, which is quite useful. So now we're going to create plots from these. So create monitor and plot from reports, and we want multiple plots. And then now we can add a monitor criterion. So we're going to create a lift criterion and a drag criterion. So what this does, we're going to create a asymptotic criterion for both. Because the problem when you work with maximum steps as your only stopping criterion, your simulation will only stop when it reaches the maximum amount of steps. But when you change your geometry, your solution will also converge at different rates. So you have to really increase those maximum number of steps so that you're sure you get, so that you're sure the solution converges. Now, if you use the drag monitor criterion, you can, and the lift monitor criterion, it actually looks at the convergence. So I'm going to make this normalized and then maximum minimum. So now it will look at the monitor of the lift, the value of lift, and if it changes less than 1 Newton over the course of 20 iterations, the criterion is satisfied and the simulation will stop. So that means the simulation will actually stop before the maximum steps are reached, and that will save you a lot of simulation time. So the drag, I'm going to make this a bit finer, because the lift will be around 300 newtons and the drag will be around 12 to 13, I think. And then the maximum steps 400, that is pretty good, I think. Logical rule OR. We're actually going to change this to AND. So, because if you leave this at OR, only one of these criterion has to be satisfied. So if the drag is converged, it will stop, but that doesn't mean the lift is already converged. So now if you put these two to AND, change these to AND, both of these will have to be satisfied. So that means the lift and the drag will be converged. And that's what we want. Okay, so now we have to have our lifts and plots. I already made a mesh scene. Let's make another scene just for demonstration. Let's make a scalar scene for the velocity. The outline displayer, I'm going to change this to a surface displayer so it displays the wing. So I'm only going to show the faces and the winglet tip. So there we go. Now for the scalar, I'm going to do the velocity magnitude, and then the parts I'm going to plot this at the symmetry plane. Okay, so that's pretty much the simulation setup. So this should run. If we click run, it should start simulating. Okay, so now we have to change a couple of things to prepare the simulation to be used by HEEDS. So first of all, I'm going to delete this trailing edge because let's say we want to replace this part. This is what HEEDS will do, so I'm going to replace this part by this step file. And as you can see, if we go to the geometry scene, the trailing edge will still be here, but it will be empty. So the edges contain all the edges. So I'm just going to delete this trailing edge, and then within HEEDS we will just execute the splits by patch command, and that way the trailing edge will be created automatically. So that's pretty much the only preparation you have to do. Okay, so now the interesting part. Now I'm going to show you how to set up HEEDS so it will automatically change the winglet shape and optimize its geometry. So we're going to make a new HEEDS study. We're going to process. So at the top you can see these tabs, and pretty much the only thing you have to do is go through these tabs from left to right, and that's the correct workflow you follow. So first we're going to define the process. So we have two processes. First of all, we have Siemens NX, where the geometry will be created. Then next we have STAR CCM Plus, and we will open our sim file. Make sure you have the correct one. Okay, so this is the correct sim file. We open this. I don't really like this auto tag feature. You can use it, but generally I just like to tag the different variables myself. So we press OK. This will take a moment to open. Okay, so now we have our two processes. We have Siemens NX to define geometry and STAR CCM Plus to simulate the geometry. So now we have to define the input files. So in Siemens NX, that's the parametric model. So again, I don't really like the auto tag feature. I'm just going to press continue. Now CAD export format, we're going to export it as a step file, and that's pretty much the NX part done. Now the STAR CCM Plus input files, we're going to use the Java macro and the step file. We can select them both and then just press continue. So also these ribbons, these tabs, you just follow them from left to right, and that's the correct workflow. So as you can see here, we have the part names. we have the subtract part, so that's the fluid domain, and then we have the parametric model. So this is the part we want to replace. Then with files, we actually have to tell HEEDS that this step file comes from this process. So we select this one here, and now we can connect this geometry to this this model. So what HEEDS will do, it will use the replace part command, and it will replace this with the step file. All right, so now we go to the macros. We want to split the edges. So we select split edges macro, and we're going to do this before the meshing. So the replacing of the parts, that's something that HEEDS will do first, and then it will start meshing, it will run the simulation, and in this case it will execute this Java macro before meshing. So now here, make sure you use the correct licensing option, because I don't have access to the power session, so if you select this, it will just give a server error that you don't have the required licenses. So here you select the amount of cores you use. I have 6 cores in total, so I'm just going to use 5. I am going to clear the solution history. You don't really have to. For example, you can do the simulation at an angle of attack of 0 degrees, and you can just let HEEDS continue the simulation from that point on. That might be useful to improve conversion speed, but I'm just going to keep it simple. I'm just going to clear the solution. So I'm going to mesh as well, and I'm going to run. So the initial steps to run, in our case, is not that that important, because the values of lift change quite easily, quite quickly. So we don't have the risk of satisfying a stopping criterion prematurely. But if you, let's say, put here 20 steps, HEEDS will always simulate for 20 steps, and then it will look to the stopping criterion. Okay, so that's pretty much it. We don't have to change anything in this. So we go to the next step, which is parameters. So these parameters are the parameters that HEEDS will use. The parameters that are used in STAR CCM Plus are separate from HEEDS. So I'm going to create 2 variables. So we have 2 types of parameters. We have the variables, which are pretty much the input parameters. Those are the values that HEEDS will change. And then we have the responses. Those are the values that HEEDS will read. So those are the response values. Those are the solutions. So variables, we have the twist of the winglet, and we have the angle of attack. And then for responses, we have 2 responses. We have the lift and the drag. Okay, so this is going to be continuous. I'm going to let it change within -3 and 3 degrees. And then the baseline value is the value that HEEDS will use for the first simulation. So I'm just going to leave this at 0. Now for the angle of attack, I'm going to let this vary between -4 and 4 degrees. And again, the baseline, I'm just going to put that at 1, at 0. Now, putting the angle of attack here is necessary to achieve a certain type of certain amount of lift. But that will, I'll explain that later on. So those are the variable and responses defined. So we go to the next tab, which is tagging. So tagging is pretty much connecting the variables of HEEDS with the variables of let's say Siemens NX or STAR CCM Plus. So we're going to select our file. So first we're going to want to connect the twist variable of HEEDS to the twist variable of Siemens NX. So we select the parts file, which is the file of Siemens NX. We select the twist variable. So now it's reading the variables within Siemens NX. This always takes a moment. Okay, so we go to expressions, and here we can see all the variables within Siemens NX. So we go to the twist, and we're going to press tag. So now the variable here, angle of attack, is linked with the twist angle variable within Siemens NX. So when HEEDS changes this variable, the variable within Siemens NX also changes. So now we're going to link the angle of attack, which is the sim file. We go to global parameters, and I'm going to change the values defined here are in degrees. So I'm going to tag the angle of attack degrees with this variable. So now we only have to tag the responses, and we're going to tag these with the lift, the reports. So the lift tag and drag tag. So that's the tagging done. Now we can set up the actual study. So we're going to use process 1, and this study will be parameter optimization. So what this means is that HEEDS will change the variables itself, will change variables to achieve certain goals. So number of evaluations, I'm just going to take 10 designs. The variables are here, that's correct. Responses here, and right here you're going to add objectives. So I'm going to add 2 objectives, one for the lift and one for the drag. So first, the lift, we want to achieve a certain lift. So we want a lift of 323 newtons, and then the drag, we want to minimize it. Now the reason why we want to have a constant lift is because drag and lift are linked. So if we don't keep the lift constant, HEEDS will just change the geometry to minimize the lift, because at a lower lift you will always have a lower drag, a lower induced drag. So that's why we want to keep this lift constant. Okay, so that's pretty much the design study setup. So now we can just run the simulation, and HEEDS will do pretty much everything for us. So we just press run. Well, we have to save the file first, of course. Twist optimization. And now it should run. Okay, so now I'm just going to show you some general things, some general tips that I found out while working with HEEDS. So first of all, you can always stop a simulation and restart it at a later time. So just to do this, you can press stop. We have 2 options, but I don't really know what the difference is, because this one, stop it, allow the analysis to finish, it will cancel the current analysis. So I just generally wait for one analysis to just finish, and then I just press stop. So if you stop this, it will cancel the current analysis. But then if we press restart, I generally don't change anything in these settings. Just press OK. It will read the simulations that have been done, and it will just continue where it's stopped last time. Now this is a simulation that I've done. So this is like 47 designs. Now to check these designs, you go to design details, and here you can just look at all the different designs. This is also a good place to see if anything is wrong. You can look at your lift monitor plot, see that everything converges. You can see here the values. This arrow makes you go to the best design. So here you can see the lift of 323 newtons is actually pretty well satisfied. And then also an important thing, because a problem that I had with this program is troubleshooting. If something is wrong, it's pretty hard to find what went wrong, because as you can see, HEEDS doesn't open the STAR CCM Plus simulation. Everything just runs in the background. Now there is actually a way to see what HEEDS is doing. So what you have to do is make sure this is selected, so show output messages. So we go to, let's say, analysis, STAR CCM Plus, and then it is working on design 2. So we go here and then we go to output message. So this might look familiar. This is the output window of STAR CCM. So here you can see any warnings, any errors that might have occurred, and you can also see where everything is at. So at this moment, STAR CCM Plus did 3 iterations. So this is pretty much the only way you can see what STAR CCM Plus is doing. So if you open this again, you can see more iterations will be calculated. Now to make plots, I might open a better one to show this. To open plots, you go to HEEDS posts. Within this environment, you have much more flexibility to create plots. So let's say we want to plot the resistance and lift curves. So we go to create plots, we do a 2D relationship. The x-axis will be our angle of attack, and then the y-axis will be the lift coefficient, for example. As you can see, then we get a pretty nice plot of the lift in function of the angle of attack. You can also show the lines so it becomes a bit clearer. So that pretty much wraps everything up. I hope this video was helpful.